So this is a supplement to Chapter 15 notes, focusing on a topic called KSP. This topic is not found in Chapter 15, but it was part of our LeShat lab, so I want to kind of give you a little bit more background. So KSP, what it's focusing on is whether or not a salt is soluble or insoluble, and we've heard of those terms before. So soluble means that the salt completely dissolves, while insoluble means a precipitate forms. But what we haven't really discussed is the fact that some of the precipitate does dissolve in an aqueous system. So that is the point that we are going to focus on with this discussion, because since some of the precipitate does dissolve, we have something called a KSP. And what that stands for is called the solubility product constant. And that is what you guys were seeing in that lab. And so we're going to discuss concentration wise how much of the precipitate does dissolve and how you can calculate that. So if we take this example, we have lead 2 nitrate plus sodium chloride makes our lead 2 chloride solid. And again, those solubility rules you're going to have to know for the AP exam, especially lead and silver chlorides both make precipitates. So when that precipitate is made, we have written net ionic equations before, but now what we're going to do is essentially flip it. So that means we're going to put the solid on the left as a reactant, and on the right are going to be your ions. And in this case, it's the lead 2 ion and 2 chloride ions. So when you look at this equation, again, right is your reactant, left is your reactant, right is your product, you could write a K expression. But remember, you do not write K, you do not include solids in your K values. So what we could do is write something called a KSP. You're going to put brackets around your lead concentration and your chloride concentration. And then just like we have seen already with K values, because there is a 2 in front of the chloride, we're going to square that. So realize that you are always going to see it in this form. So you're going to have the solid on the left and your aqueous ions on the right. That's going to be the standard format for how you see these equations. So realize that the KEQ we've been discussing, or KC, is the same as your KSP if A is ionic. And that's all we're going to be focusing on in this course. So you will always see solid on the left and aqueous ions on the right. So you're going to hear some terms in this section, and then when we conquer this again in chapter 17, which is something called molar solubility. And all you need to know about this term is the fact that you're talking about molarity. So realize that these are all going to be at equilibrium, and so that is why it is go forward and reverse. We're talking about in water at this point. We will discuss if it is in some other solution, and realize that salts have a certain solubility at 25 degrees Celsius. So again, 25 being the standard temperature that we look at for things. And these are the terms we've heard before when we were doing a solubility curve of saturated, unsaturated, and supersaturated. Again, we are going to focus on the fact that it's probably at some state of unsaturation, because you do have the production of the precipitate, but you have very little of the ions. And I'll show you how small these numbers are. So let's work the problem you have in your notes. I have a KSP value for iron to carbonate is 2.1 times 10 to the negative 11th. And these are going to be standard numbers that you're going to be given. You're going to find the solubility of this salt in moles per liter. So the first step you're going to do is essentially write the KSP expression. And all you have to do is look at the salt and say, okay, how many ions do I have of each? So I have iron 2 and I have carbonate. So I'm going to multiply those two together because they are in a 1-to-1 fashion in its formula. So the KSP is then going to be, since I do not know the concentration of those ions, I am going to have them as my X. But typically what you will see for KSPs is they sometimes do S's. So that's why I have it here in the slide. It doesn't matter if you write X's, but if you see that in the future, it's not foreign to you. So of course, if my KSP value is the 2.1 times 10 to the negative 11th, that's going to be my S squared. So mathematically, you take the square root of the 2.1 times 10 to the negative 11th, and you get 4.6 times 10 to the negative 6 molarity. And since S, your X, is in a one-to-one relationship, meaning you have iron 2 and you have carbonate in a one-to-one, that is essentially your solubility of those ions. And if you look at that number, 10 to the negative 6, that's a pretty small number. So again, we didn't really talk about this before. And the reason for that is because these concentration of these ions are relatively small. But when we get to acid-base chemistry, we will be talking about the fact that you can see these ions in solution, and you could change how this equilibrium behaves by changing its acid-base qualities. So that's one example. And this one is, of course, a one-to-one. So what if the salt was not in a one-to-one cation to anion relationship? So we have the KSP of calcium fluoride is 2.7 times 10 to the negative 11th. Again, that number will be given to you, and I'll show you where you could find it in your book. So you want to find the molar solubility. Again, that's just a vocabulary word. It's molarity. And what you were trying to do is find the molar solubility of both of those ions. So again, the KSP for this will be calcium ion times fluoride, but the fluoride is going to be squared because you have two of them in the equation. So if we were to write this equation out, we have the calcium fluoride solid is breaking up into calcium ion and two fluorides. So again, the 2 is there because of the fact you have two of them. But what is sometimes it feels like you're doing double duty here is the fact that if you're looking at concentration of calcium versus fluoride, think of it in terms of a beaker. You would have calcium and you would have twice the amount of fluoride floating around in there. So that is why if you have a concentration of calcium, it would be twice the concentration of fluoride because of that. So again, think of it in terms of these ions floating around. So because that is the case, this feels very redundant, meaning that fluoride, everybody's okay with the fact that that is a squared term. But what seems weird is the fact that it's going to be 2 times the concentration. But again, we're talking about if you're swimming around in that beaker, how often would you see calcium versus how often would you see the fluoride? So you would see the fluoride twice as often as you would the calcium. So that is your concentration term. So mathematically, that turns out to be 4s cubed because the 2 is squared and you have the s squared term. So to solve for this one, you are going to be dividing by 4. And once you divide by 4, you're going to take the cubed root. So what you will get is 1.9 times 10 to the negative 4th molarity for your calcium. But you have to recognize that since calcium is the x, fluoride is 2x, well, if I want to know what the concentration of the fluoride is going to be, I need to multiply it by 2 because it is a 2s. And that's the only difference between the first example I showed you and this one, is the fact that the calcium fluoride is a 1-to-2 relationship with its cation and its anion. So that's the only difference. You won't see anything beyond 4s to the 3rd on the AP test. You will see some examples, but it's never going to be tested. So one last thing I want to conquer here, and then I'll be done, is the KSP values. So in your book on page 1004, there's a list of KSP values, and you could type into Google and find KSP tables for some common salts. So I want to talk about these two examples of silver iodide and calcium sulfate. And these numbers are in the table. And as you could see, one is very small, the silver iodide, compared to the calcium sulfate is 10 to the negative 5th. So a question you're going to be asked is which salt is more soluble? And all you have to do is look at those two numbers and figure out which one is the bigger of the two numbers, which in this case is the calcium sulfate. So the bigger number, 10 to the negative fifth, means more of those ions are floating around in solution in comparison. Okay, so just comparing the powers of 10 here, you can look at which is more soluble. Now, another example of this would be comparing copper 2 sulfide to silver sulfide. So I have 6 times 10 to the negative 37th, and this is 6 times 10 to the negative 51. Again, looking at those two numbers, you're going to be asked which salt is more soluble. So if I look at 10 to the negative 51 here for the silver sulfide, I might guess that the silver sulfide is going to be more soluble, but we don't really know that. And because of the fact that copper and sulfide is in a 1-to-1, and this is a 2-to-1, I can't compare. So because I have the different number of ions, this is not a useful thing. If I wanted to compare them, I would have to do the actual math. So the copper sulfide would be an S squared situation because you have a 1-to-1, while the silver sulfide would be a 4S cubed, and I would actually have to calculate the S's to see which one is a bigger value. So that gives you at least a beginning introduction to KSP to help you out with the Lee Schacht lab, but we will also be discussing this later in Chapter 17.